again, I can introduce two really veteran troopers, Sergey and Big Easy, that will give us a talk about adventures in SCADA system. I think SCADA systems got a lot of attention in the last year, think Stuxnet. So I think they have some very interesting stuff to tell. And I heard some rumor the talk also has something to do with cheese.
We have cheese.
Yeah, I deny it. I deny it. Cheese is not on the top. No, no, no. All right. I'm Sergey Bratus. I'm a research assistant professor at Dartmouth College. And before we plunged into SCADA, I would like to...
what about me?
Oh, yeah, you have to.
Sergey?
Absolutely, absolutely. I was going to talk about the Dartmouth side, then introduce you.
Oh, well, I'm sorry. Go.
All right.
Go,
well,
then go ahead.
Absolutely,
no,
absolutely.
But
like you're going to be associated with cheese, that's right. Big Easy, who is the reason, Edmond Rogers, who is the reason why I was actually able to get this wonderful adventure in SCADA. Big Easy worked for a Fortune 500 utility company, protecting a control network, keeping the lights on in N states, where N is...
greater than 0 and less than 50.
All right, you know. So you can imagine. So before we start on the SCADA angle, I would like, as a public announcement, and to show some value in academia, so to say, I would like to talk about two projects that we have at Dartmouth.
Wait, we didn't discuss this when we were going over the slides an hour and a half ago.
Indeed, but it has nothing to do with cheese or SCADA.
Okay.
So one is Crawdad. This is our repository of wireless data. If you want to be immortalized, or your data set to be immortalized, give it to us. We are proud to host the Next Hope New York Hacker Conference badge data and many other interesting pieces of data. That's one project. The other is the project that Anna mentioned during the keynote. We're looking to talk to CISOs to determine how they bridge the gap between the technological underpinnings that systems can enforce in terms of policy, attestation, trusted computing, anything that Intel and other vendors are throwing at the security wall, and how this is meeting or not meeting your needs as a CISO. And with that, we're coming back to adventures in SCADA. So we have a varied set of interests, which is what found me going to a SCADA place. In most SCADA talks, you actually see images like that, and they're there for the show. I actually got to see that kind of a board. To lead in, and now I have to totally disappoint you. This talk is not going to release any 0 days. We're not going to name any vendors. In fact, this guy is going to...
I'm here to ensure that.
Yeah, basically jump on me if I do. And there is going to be no Stuxnet. No Stuxnet whatsoever. I mean, Stuxnet is a load of fun, you know, and made this guy very unhappy. He probably doesn't approve that we're not talking about it. But, you know, we're not playing, and there should be a Stuxnet bingo. But if you're interested in Stuxnet, there are two great talks in the CCC 27C3 this December. Chase them down. They're very informative. It was a revelation to me. So we're not going to talk about Stuxnet, but we are going to talk about SCADA in the wild. And most great talks in SCADA vulnerabilities, which actually released 0 days, unlike, you know, I'm not going to do today, were researchers taking open source SCADA, setting up some sort of an artificial test bed in which they could talk to it, and then exploiting it. What we got to do was completely different. First of all, we wanted to see the really expensive pieces of equipment that are working at an actual utility. Secondly, we wanted to go there and see what a control network looked like on the inside, and what that environment looked like operationally. And besides, it's cruel to take something from a SCADA piece of software from the wild and bring it to the lab, and they don't breed as well, and it's just, well, you know. So it's better to go to the jungle than build your zoo, possibly, maybe. We did do some fuzzing. We're going to talk about that. The interesting point about fuzzing with really expensive, and we're talking $100K to possibly $1 million, is that you can't instrument those things. No way. And the vendors are not going to give you the spec. And the bonuses included going through this a kind of a man trap.
Anal probe.
No.
Sergey doesn't like to talk about that.
No freaking way. Anyhow,
it was easier getting through the airport?
No peeing in the cup either. Absolutely. So as you know, for many jobs and access to facilities, people need to do drug testing. So no, that was not one of those.
And the biggest thing was Sergey had to get up and be ready to go by 7 a.m.
God, SCADA people, right? They're up at 6, at work at 7. If you want to play ball with them, you have to be up at 6 and in at 7. This is horrible. Fuzzing across state lines. We're going to talk about that. One piece of equipment is installed in the next town over and possibly in a different state. And what do? You need to you know, work with that. So this is what we got to do thanks to the trust we build with this particular SCADA vendor. So just a little bit of an introduction, since I did not quite understand what control networks looked like. So the way it goes is approximately like this. First of all, a power company is a company. And so it needs to have a corporate network. Moreover, power companies in the US are deregulated. They trade electricity. So there are salespeople sitting there. And, well, and there are all sorts of interesting things that go on in that network, which you want to keep the hell away from lolcats, zombies, phishing. You want to keep that the hell away from your control network. Secondly, there is a control network proper, which...
You're doing good, Sergey. Keep going.
Yeah, which includes things like energy management servers, control boards, data historians, where the data is collected, all sorts of state estimators that process the phase, current, voltage data that comes in from the field. Now, this looks pretty close, right? But those substations, those sensors, can be placed hundreds of miles away. And this line may be basically a modem line. So SCADA kind of looks like this. Can you actually see?
There's supposed to be a dinosaur under the house.
Well,
I told you should have used GIMP.
Well, imagine, if you will, that there is indeed a dinosaur right under there.
OK, let's move on.
Let's move on. So very often people talk about substations in the cornfield. And as I Googled for such a picture, I actually found this substation building. Oh, you can see the electric tower mast here. And it's actually located in Cornfield, Illinois. So you bet. And inside that substation, you would find an old modem. 9600 is actually fast.
High-speed modem.
Yes, yes. And that goes over a leased line back to your nice cloud of control network. And these are really old modems, but reliable. You know, this is what you want. Dependable. This is what you want to depend on if you care about keeping the lights on. So all of these lines come into a modem bank. Oh, the screen is really dark. This is too bad. You would be able to see the little modems.
There's a bunch of modems where it's black.
Mm-hmm. And all of those modems are driven by a specialized computer, which is basically not so very specialized. It's x86 running Windows or Linux nowadays. That machine is called a front-end processor, or FEP.
Yeah, and one of the words I really got freaked out about when I first started at the utility was modem. They're always throwing this word around. We have all these modem connections. And from my mind, from, you know, growing up in the 80s and being a hacker back then, modem was like Woody time. And I'm like, what do we do with all these modems? But they're not actually modems. They use from my telecom background, I would use CSU, DSU. These are nailed up 4-wire circuits. They're closed circuits. They're not modem circuits. It's not like all of these substations have telephone lines that you can dial to access the front end from the other side or the actual substation. These are all nailed up lines on just the plain old telephone network.
But imagine my surprise when Dartmouth, to my great regret, got rid of its modem banks. And here I come to this utility, and I encounter a guy who's running a word dialing operation, a major word dialing operation. OK, so and from here on, it gets a lot more and more fancy, more and more modern. A front-end processor, or several of them, will talk to an energy management server. This sort of a machine, again, would be your commodity machine, rack-mountable, running state estimator software and other specialized state of the health of the power grid software that tries to solve a whole bunch of differential equations. That, in turn, talks to the large boards where the actual operators can control the electric grid. And you see that these communications are over switches, but in fact, they're very likely to be over routers, and the control room may be in a completely different physical location. So the system like that is extremely expensive to build. For individual units, we're talking 100K, and that's an understatement. For an entire system, even for a small one.
And then, you know, before our adventure started, one of the things that was when I came into the utility business and got involved in a lot of compliance work, they were always throwing around trust but verify. So I came up with a really cool idea. I've got millions of dollars worth of SCADA gear. I'm going to do some trust but verify, and I'm going to bring in researchers to have them look at this gear and tell me, you know, what's going on under the hood here. And then people like Sergey were like, whoa, that's going to be awesome. And he's totally getting into this. He's like, he thinks he's in heaven. It was Christmas for Sergey. And and one of the things I really wanted to get involved in doing about this was because I'm a paranoid person. And I wanted to validate some of the mitigating controls that we were using on the control network. Because we did a lot of freaky things that may seem a little draconian to normal users of a Windows network system on the control network.
In fact, this was one of the most paranoid networks I've seen, although I hear that not all utilities are that way, unfortunately. But this is the kind of a paranoia that, on your behalf, that you get to really appreciate. But anyhow, what really surprised me is that utilities may spend a whole lot on mitigation of issues with that equipment as on the original equipment. So you can imagine, if the original things cost upward of $1 million, then what are the maintenance costs? So we could not, of course, mess with the network that keeps the lights on.
That's not a good idea or recommended at home. You probably should never fuzz an actual live production network.
So instead, what happened was a number of devices were taken into this test environment that connected them into an isolated network topology, isolated from the cutoff from the production network. But what we had right was the geographic distance. So when I'm talking about fuzzing across state lines, I'm not joking. The fuzzer was in...
This is a sample. This is not the actual cities involved in the experiment. Sergey wanted to put a little map up, so I'm going to be going to, I'm in Champaign, so this is kind of like the idea. The whole idea behind was we have an insider who knows a lot of shit, and that was like Sergey's job, and I'm like, well, what we're going to do is give Sergey an Ethernet port inside this network we build for him that is it's a representative network, exactly like what you would see in a control system environment. And then we did some funky stuff with VLANs and things like that so that he could do his research across a wide area network.
Mm-hmm. So these are actually affiliated organizations such as the University of Urbana-Champaign, and there is a power co-op in Springfield, but yeah, not the actual locations. Sorry, I can't disclose that. So what you want to do to test the brittleness of the system is, well, of course, a whole bunch of things. But the easiest thing to do, and the thing we did, was, of course, fuzzing. So fuzzing is not in need of explaining, but I thought I'd just yeah, illustrate the general principle. You craft inputs, and yeah, fuzzing SCADA is just about as hard as toppling intricate structures like that once you get to the actual equipment, to the actual network port. And moreover, people have been doing that. But again, so for example, Ganesh Devarajan gave a talk that made quite a bit of a splash at Black Hat 7. The media ran with it, but the media runs with everything. He wrote a DNP3, a popular control protocol module for Sully the Fuzzer. Digital Bond did an ICCP fuzzing test suite. This is what you would have utilities communicate between themselves, and they release it to vetted asset owners, that is to say SCADA operators. There were some freer releases that targeted parsers for the DNP3 protocol inside Wireshark. As you can imagine, the same protocol would need to be parsed by an actual target device. Mu Security makes a great business selling the hardware appliance. You know, your SCADA device Ethernet goes here, and it talks to it, and you pay on the basis of protocol modules that you want to test. So all of those things, though, operate for specific protocols. DNP3, Modbus, 61850 family of protocols. What we needed what we had to deal with is proprietary protocols. So we were not going to be told which protocols were running on that SCADA network. And even though I knew a sort of a manual existed, and I was shown it from the distance, with Edmond having to hold on to it, I could not see that. So we could not bring the best possible approach in fuzzing, that is to say, fuzzing based on the protocol model with modules of the kind of spike. Moreover, the thing about fuzzing is fuzzing for exploitation is that you get to instrument the target, and actually you have to spend quite a bit of work making sure the target restarts and enters the right kind of a communication so that you can feed your crafted input in it. So who's going to let us instrument a piece of equipment that costs a whole lot and that you can't that you can't void a warranty on? And who is going to restart it for us in the next town over across the state line when it crashed? And so apparently we have a problem. But in fact, we don't have a problem. And I can't do a convincing King Leonidas impression, but this is SCADA, right? This is different. This is a different world, as we found out. So first of all, you can learn what the protocol data structures look like because they are transmitted continually. That thing in the substation that's talking to the energy management server, the energy management server talking to a control station or the board, they are sending the same thing over and over and over again. And that data is very similar. Moreover, if you manage to crash it, a watchdog will automatically restart the control process or reboot the system if you manage to crash the system. So this is great. This is taken care of. Moreover, those things keep sending messages, keep alive their status, so you can actually see when you succeeded in crashing one because these things stop and there are TCP resets or SYNX or other indications of attempts to restart the connection by the watchdog. So it gets better because quite a few of those protocols have this distinct handshake that establishes the data session and then lets the data flow in the connection. So you can wait until that happens. And if you can get in the communication, which you do by the way of any given man-in-the-middle attack, then you fuzz the data. Then you're getting at the insides of the business logic of those things. And it's actually pretty much similar data. So if you're doing mutational fuzzing, you have pretty good coverage because the same piece of data will be crossing the network pretty often, and you can mutate it differently. So for mutational fuzzing, this really, really helps. And so the standard approach that people take to mutational fuzzing is probably exemplified by GPF, the General Purpose Fuzzer, VDA Labs. It's open. What it does is it saves network protocol sessions. So you've got a PCAP file, nice packet capture, and then you replay it using heuristics for inserting large runs of ASCII characters or large runs of unbalanced, what do you call those things? Parentheses, you call them delimiters, yes. And then you observe the target and see if it crashes. That wasn't quite what we needed to do. We did not actually want to save those sessions. In fact, we probably would not be able to, and I would not be able to walk out of there with packet captures in my pocket. So what we needed to do additionally was bring back some of the spikiness. The approach that David Eitel first discovered, Spike, is just about the first block-based fuzzer. You start with the model of a protocol, and you generate it block by block, field by field, and you mutate those fields, you fuzz those fields heuristically based on what is likely to crash the recipient. So you do that to get past the first sanitization stage, past the first sanity check of your target to get to the business logic. So what we wanted to do was first fuzz data in transit with something like GPF, but guess blocks of the unknown protocol. Just enough to do better. And there was a little scientific idea or a dirty hack, depending on how you look at it, that occurred to us. It was, there is a thing that counts repetitive tokens, repetitive substrings in communications. And it does so in order to compress files. And Lempel and Zeev came up with that quite a long time ago, the fathers of modern practical compression, you might say. So we run a variant of this algorithm. We don't compress anything, but we accumulate the same string table. So, and we seed it with an initial set of packet captures. And then to those repeated strings, we assume they are tokens. We apply the heuristics. And so architecturally, it looks pretty simple. Here is your IPQ. Here is your man-in-the-middle attack. We found that our poisoning generally worked, which was a bit of a surprise. Of course, in order for us to get there, a whole other layer of security that included IPsec had to be rolled back. But an interesting observation was layer 2 security is too expensive. So the things that you do, they would get in the way of quickly recovering the network under the circumstances that you would want to recover it under if the lights are out. So, but there are other emittance, of course. Once we have the packets flowing through us, and of course one of those mittens was against the gateway so that we could see the target the next town over. They're handed to IPQ. Through IPQ, they were given to a Linux user land per packet tokenizer that I just described. Through that, they were fed to a modified GPF so that it could deal with packets on the packet level rather than with sessions. And so it worked. So as a recap of the technical issues, what was really needed was looking for signs of the target crashing and backing off so that the connection could become reestablished by the ever so watchful watchdogs and by the ever so helpful modules that restarted those connections on the servers and front ends. So we have a whole bunch of rules. The simplest involve looking for resets. Well, obviously, you crashed the process, so your further TCP traffic to that port is going to be rejected. Repeated sins, special auth handshakes, and those regexps were not allowed to release, obviously, because the vendor insisted on the protocol becoming as closed as possible. And timeouts. So with that, you can actually get pretty good coverage of most standard protocols. Because if you are sure you crashed the target, you just move the window of fuzzing, and you proceed. And so, it's not the smarter ways that people fuzz for vulnerabilities, but it gets pretty good coverage. One problem is that you must find the checksums and recompute them. And you can do that with a bunch of other tricks. So in the end, the more developed version of the fuzzer that we're working on now and have almost done includes things like fixing TCP sequences when you inject extra TCP packets to accommodate the longer fuzzed payloads. Then there are custom rules that identify replies and identify the authentication sessions. And then there is a tokenizer mutator. OK? So how does that do? It's a bunch of heuristics, right? Well, we could obviously not instrument SCADA gear. But we instrumented a couple of things, a streaming protocol and an IM protocol, thinking that they might be roughly about the same things. So DApp used by iTunes and Oscar used by AIM, instant messaging. And so you see, this is what you get. This is the code coverage, which we could instrument, of course. This is what you get with random fuzzing, random mutational fuzzing. This is what you get with GPF unchanged out of the box. This is what you get with our lazy fuzzer. No, wait. This is what you get with our lazy fuzzer. There, I'm colorblind. And this is all of the code running in unfuzzed stage. With game, we were under fuzzing, but probably actually not under fuzzing. The problem was that as we restarted the sessions, we could not exactly replicate what the sessions were. But basically, you know, we did better than the GPF, which was, and much better than random, which was good. So we validated our methodology, which was the only phrase I was allowed to say about the whole engagement for a while.
And then Sergey really touched on it just a little bit in, when he was going through the actual fuzzing part of this, but one of the other things that Sergey really had to struggle through was the weight and the measurements that we were taking when we were determining how long it would take him to be successful with all the mitigating controls turned on, which Sergey was not able to successfully fuzz the network with the mitigating controls turned on.
Well, I did not have the IPsec key, and I was not allowed to exploit anything that was connected to the network. So,
well, he had a few stumbling blocks. You know, he had some handcuffs on, but one of the things we really wanted to do was check and show that the mitigating controls that we use to prevent bad things from happening on the network, because one of the things we're very concerned about is the insider threat and the USBs of the world and people bringing in stuff and plugging it into Ethernet ports that we may not be able to control underneath someone's desk inside a closed room. And it was nice to have the paranoia justified, because when we do turn back the mitigating controls and lift open the door a little bit for someone like Sergey to come in and fuzz, there was a lot of people concerned about their careers if we ever did do a full disclosure on what we found.
Well, so as you realized, right, this is not about fuzzing per se. This is about being able to inject into the network, right? And of course, fuzzing is only a stand-in for real exploitation that is enabled by injection. So mitigating controls, isolation has all the reasons to be paranoid.
And then it was really good for us because Sergey got a chance to validate his science. At the same time, from a corporate perspective, we got a chance to better communicate an understanding of why certain mitigating controls existed on this network, because they're very cumbersome to people who don't understand why this is so important. It was very successful on both the business side of the fence and on the scientific side of the fence. And then it's been a while since it's happened. And one of the things that, as this has been in the past, and we did the research and nothing ever came out from it, it's really a success story about how academia and industry can work together, and an academic can get his papers published and not necessarily interfere with the reputation of any businesses that may or may not have been involved in this research. We tried 0 and 50 states.
Yeah, we tried to walk a fine line, and you know, hopefully we'll be coming back. So, one really good question is, what is the role of full disclosure in this? SCADA, arguably, changes as an application, changes the game for full disclosure quite a bit. The idea being that, well, you do not find SCADA devices in the hands of the general public. It's not your iPhone. If you publish a SCADA advisory, it's kind of hard to make the argument that a SCADA exploit. It's kind of hard to make the argument that you are somehow exposing the naive and the guiltless common user who cannot be expected to take protective steps to a paranoid level. Your SCADA should be run by people who are professionally paranoid. Your vendors, on the other hand, would not appreciate it at all. And even though big power companies buy a lot of gear from them, and so as big customers they have a considerable pool, it's really not as easy to get a vendor to release a patch. Maybe a war story?
Well, it's not that. The whole idea behind patching in these types of systems is multifold. First, you have to get the vendor to develop the patch, and they have to go through their own QA process before the patch is ready to go. And then the vendor really needs to make a decision about whether or not they're going to let the patch be released. And then even after that point, as a utility or a keeper of critical infrastructure, you need to decide when it's going to be a good time to install the patch. And then one of the things you always weigh when you're deciding about whether or not you're going to patch is what other mitigating or compensating controls do you have to possibly delay the installation of the patch. So there's a lot of complex things involved. When you have a system that always needs to stay on, how do you patch something like that? It's not like every Tuesday we can turn off the electric grid for 2 hours so we can reboot all the systems. So
I was happy to give the ammunition that Edmond needed to talk to a particular vendor who has been recalcitrant on those things. Now, the vendor, now I was not allowed to take back the crash dumps, but the vendor was phoned and informed of this thing that was suspected to be quite brittle, remaining brittle after a number of patches. The next day, a vendor representative came in from thousands of miles away.
And they had to be in by 7 a.m. too.
And we were in the room, and they were basically doing the vendor response of calming things down, you know, trying to talk this down, and I was enjoying the proceedings, I must say. So,
They had good cheese.
I didn't get any of it. If I did, I deny it.
They wouldn't let Sergey
I wouldn't be able to.
They wouldn't let Sergey keep the cheese.
Yeah, remember the man trap?
They took the cheese home with them.
Yeah, that thing is real. You know, it was a weird experience coming through that thing to get to a network port. But hey, so let's look into the future. The future is going to be this wonderful, much more reliable, agile, smarter grid, maybe. Or maybe it's going to be this long struggle through political visions of the bright future, but the way is all strewn with rakes and, surprises. Or maybe, as we get progressively more dark and paranoid in our outlook, maybe some really bad things would happen, right? The way we normally do engineering is by putting things together, composing things, but some compositions are deadly. In fact, the greatest wisdom about security from the academic point of view is security is not composable. If you forget anything that ever came out of the academic science, remember this. Complexity kills, as Anno likes saying, and I really like that quote too. So, and of course there are wrong threat models. You know, what is going to get you? This thing is supposed to be real, right? So here's your corral, here are your horses, and this thing comes out of the blue. Apparently, such things were real in South America, and there are fossils to prove that. So,
what's that word, Rodrigo? The word you taught me yesterday. Joselito, yes.
Anyhow, now, with all the hype about the smart grid and every bit of media, every 2-bit journalist writing up a storm about how it is going to improve life and solve all of our energy dependence problems and somehow improve the climate 100 years into the future. You have, when you talk to a power guy, when he says it's smarter grid, thank you very much. The grid is already pretty smart. It has a whole bunch of sensors. It has a whole bunch of other software and hardware pieces that take advantage of those sensors. But it is going to get larger as meters and phasers are going to be rolled out through the actual power grid. In fact, the biggest money may not be in smart meters. It might be in all sorts of sensors. Figures being discussed are tens of millions or hundreds of millions, but it's clearly going to be a lot. A whole bunch of vendors are very keen on replacing the current controlling elements of the smart grid, like relays, with what they call intelligence electronic devices, all rolled together in various compositional ways. And so you have this problem. How do you secure 100 millions of devices? And it's really a to be or not to be question. The first issue that looms once you step out of an academic setting and talk to people who run networks in the world is how do you remotely administrate and whether you can actually afford to remotely administrate all of those things. Then the network environment is almost certainly going to be the internet. Arduinos now make toilets tweet, and you can not find any class of a household appliance that has not been connected by one way or another to the internet by way of a radio. But do you trust that environment to carry your packets? How do you trust the identities in that environment? And will the solutions like authenticating solutions scale up to that scale? Trust is the primary issue in the grand plans of smart grid deployments. How do you extend trust to hundreds of millions of devices or, in a particular deployment, even if it's a million for a big utility? If you can't trust them, what good are they? How do you keep all of them trustworthy? We talked to an operator of a large electric utility, and they realized that they could not pay for the bandwidth from a big ISP because the ISP quite reasonably as it turned out, wanted peak rates and huge bandwidth and latency and fees for keeping the latency low enough to make this a reasonable SCADA control environment. So they realized that they would have to build their own network. They could not afford the structure of those fees.
Whenever you scale any kind of solution that you find in a more modern world, like where I worked at, we had a smart meter solution basically where the meter had a cell phone tied to it and it would phone in usage data. So we have 1 million meters out here that do this. When there's an outage, what happens when 1 million cell phones make a phone call at the same time? You have a massive denial of service attack on the phone network. So your carrier gets all mad at you because this happens. So you really don't get a lot of the data in a timely manner when you need it, when you have all these devices. It presents a lot of interesting problems about you almost have too much data to get it in a timely manner. How do we extend trust, get data where we need it from in a timely manner so that we can make decisions?
Moreover, ISPs tend to believe that if you buy more bandwidth from them, it will also improve your latency. Now, your latency doesn't matter that much if you're doing what their customers mostly do, which is download, watch video, play games. Games are actually tricky. So my wife, who is a maintainer of Crawdad and an avid game player, Anya, wave, is my latency sensor. the moment something interesting is happening on the network, despite the bandwidth being just great, she detects it when she's playing. So ISPs may not be able to continue solving latency problems, latency requirements of SCADA by just doing what they usually do, throw more bandwidth at it. Of course, I love referring to this Dengier address at Source Boston.
And this kind of like talks to what I was just talking about before. You know, we've got basically right now a one-way network out to the home meter. You know, what happens, and then what are you really buying if you can get remote administration or you can push data out to the meter when you get 80% of the information you already need from a one-way communication out from the home. So when you start getting to a situation where the meters are remotely accessible, then you've got interesting ideas about people who can actually update firmware on those devices because they're able to accept data coming in.
And it's an evolutionary argument. Organisms either adapt to changes in environment, that is to say, their firmware gets upgraded, or they die.
And then there's a more practical problem about, you know,
how do you commission them? How do you put them in place?
How do you maintain trust? I mean, how do you trust 100 million devices?
Well, one way is, of course, cryptography. It is said that we're pretty good at using key-based cryptography to authenticate things, except maybe not 100 million things at a time. So authenticating things requires sharing a secret or a key, at least, with every device in the environment. And just exactly how do you do that? If this is a human-bound operation, then it costs a whole lot of money. If it is a remote automated operation, you have a huge attack surface. So a really interesting observation that came to us from another utility operator has been that they went the way of PKI for authenticating their devices. They found that at a certain scale, the keys, the ephemeral bit strings that go on those devices, cost them more than the physical devices themselves, with all the electronics and all the kit and caboodle. So, and that was not a very successful PKI deployment for them. Managing this shitload of keys means being able to replace them when people lose them, being able to revoke them, being able to support the owners who can't get to do what they want to do. So this is a huge problem, and I posit that it is not entirely solved. One reason why securing those kinds of network is hard is that you want to protect the link layer communication. In fact, the 61850 popular SCADA protocols are originally designed for layer 2, broadcast medium, multicast medium. Now, in order to secure layer 2, you need to get keys onto devices. You need to engage them in cryptographic protocols. Implementing cryptographic protocols in layer 2 without sockets is not a pleasant thing to deal with. So programming with frames sucks. Programming with sockets is just about how the internet happened, how most protocols are implemented, how developers are trained. You need a whole bunch of developers. So there is this crypto chicken and egg problem. If you need layer 3 to distribute keys and run an authentication protocol, you have to do it before you've secured layer 2, right? So what gives you that layer 3? Layer 2 already has to be under it. So it is a chicken and egg. And finally, you want to keep, there was your C in confidentiality. How about integrity in the famous CIA triple. How much is it in terms of energy cost to maintain 100 million computers doing whatever computation they need to do in order to check their own integrity? I mean, your power meters are running. That CPU cost is not free. Pushing patches to those, you need some really fat pipes. And finally, if you want to go the way of TPMs, so here is the march of TPMs, Trusted Computing Group, right? That is probably so far the best that the hardware industry can offer in commodity devices. But how do you maintain a wide list of trusted configurations? How quickly does that blow up? It's a really good question if we have the engineering ways to address those problems yet, if we still understand them. Or maybe we'll have to discover them. Let's hope we will not have to discover them in the traditional way of stepping on them and going. Yep, it hit us again. So thank you for your attention. And while we still have less than 3 minutes, we'll take your question. So sorry for the non-disclosure and no vendor blame, but I want to come back there. I became sort of attached to that man trap.
Sergey, big easy. Thank you very much. Questions?
So, Sergey, did you manage to trip any switches and turn off things you shouldn't do?
So part of the, okay.
Okay, big easy, let us have a beer.
Cheese!
You get a piece of cheese for that.
There you go, yeah. Part of the reason, I mean, we spent, once we got our MITM, and once we had a reasonable degree of control over the topology, we spent, this was the only loud thing that we did. We spent the next hour listening and trying to understand who was talking to whom, and what protocols were in use, and what that meant, and what other front ends might have been there, what other energy management servers were there. It was an isolated environment, but it was a big environment.
You know, and we said that it's all about defense in depth and how deep the hole goes. When you're there and you're in between and you make it to the middle, these are not very maturely coded systems. So you can imagine what you could do if you were so inclined.
But it was a fun exercise. You know, basically, we had a phone line with. Was it a phone line, or did we have? Did they have a remote access to that machine as well? You remember when we when I would try switch a different fuzzing mode, and that person would say, you know, yeah, another crash.
We had console access.
Right. Here comes the blue screen.
To the machines.
Yep. So, you know, it was an interesting experience. And of course, you only want to crash the things that people want you to crash. If it's a trip if it's a drive to the next town for them, to reset that thing. Or
and the more interesting things don't really result in crashes in the first place, because if your control system crashes, it's going to be noticeable.
So, it was...
And the lights don't go out when the control system crashes.
Yeah.
The lights stay on. The power grid is more resilient than that.
Yeah, this is actually one of the major media miscommunications that they need to be called on their bullshit. The power grid was built before computers, strictly speaking, and it has ways, electromechanical ways of protecting itself and of running itself if the more controlled, if more control involved in trading or final load distribution is not available.
You can close breakers, you can shut things down from these systems, but these systems are not necessarily required for the grid to operate. It can be done without these systems.
It would be a really bad thing if they hadn't.
But it would be like Marty McFly in Back to the Future. He'd be going back to the 50s without a cool DeLorean.
Just what you said, I mean, if you go ahead and scale the system itself to the scale you want to have with renewable energy power and things like that, then suddenly you're probably relying on those SCADA systems all the time, aren't you?
Yes, and it's a good comparison is probably flying by wire. A modern aircraft at some point reached the modern performance aircraft, military aircraft.
And some of the more challenging things along those lines are thinking about all of this stuff that's coming onto the grid that can produce electricity, but not in very large amounts. People think about 1 megawatt as being a lot of electricity, but it really isn't on the grand scale of a grid as big as maybe the Eastern Interconnect in the United States. But if you've got thousands or hundreds of thousands of different little small solar arrays or wind farms, you don't know where this electricity is going to come from. You need a lot more information in a short amount of time, because these systems need to solve the state of the system. They do this every 6 seconds. And then it needs to get more and more data in, and then there's some more sophisticated data that's also involved. And then, at least in the United States, there's also regulatory requirements that if you make real-time decisions based on information that you receive from the field, then there could be certain regulations that then apply to these systems, which are very costly. So there's a lot of compliance and business issues with the emergence of all this routable data that's coming in from the field.
So the just like I said, if your plane that's fly-by-wire, that cannot be flown by a human because of its aerodynamic instability that makes it so agile in the first place, if the wire goes, well, the plane goes. So, God forbid we get cars that are drive-by-wire, right? My truck has 7 computers in it, and I'm not enjoying that thought. Not at all.
No, there was a cheese for you.
I think last question.
Yep.
So from your fuzzing, you know exactly what values were causing the crash, or did you only know approximately? And were
Yes.
you allowed to follow up on that? Were you given the information or access to determine what the problems were, so that you have a good picture of what the actual problems of these systems are?
Yes.
Yes.
But you can't just talk about it. That's it.
Vendor has been given full report with specific packet captures that their systems barfed on.
So that means anybody who has written something like Stuxnet is an insider, right? I mean, even you didn't get the information.
People who wrote Stuxnet, I mean, look, compared to the complexity of Stuxnet, our little fuzzer is, it's decidedly kindergarten, right? So yeah,
The people who wrote Stuxnet had access to the manual that we didn't have when we did this experiment. Is that a good way to answer the question, Sergey?
Yeah, they had the access to the damn centrifuges, most likely.
Okay, so some more rumors were born about Stuxnet.
Yeah, no Stuxnet. No Stuxnet.
We said no Stuxnet in the talk. We're not here to confirm or deny anything about Stuxnet.
Yeah, no Stuxnet. Yes, okay. But do watch those 2 talks at the Chaos Communications Congress. In particular, they covered both sides of Stuxnet, both wonderful pieces of engineering that went there. One, the Windows 4.0 days that were so well engineered and so cross-system that is just amazing. That's a guy from Microsoft. That's the first talk. The second talk is by Felix Lindner, FX. He wrote his custom disassembler for the PLC code. And in the process discovered some things about the PLCs that the Stuxnet designers themselves might have missed. So this is a fascinating talk. which led him and other people to believe that the authors of Stuxnet might have actually been using the Siemens SDK as opposed to their homegrown SDK. On the other,
Sergey, thank you. I have to hurry up a little bit because we will continue at 4 p.m. If you have more questions, feel free to talk to Sergey and Big Easy. I don't know if they have some cheese left, but I am sure
cheese,
they will also
forget cheese,
take questions.
beer. Okay, beer. Beer
Rodrigo.
does it.